Blow up a balloon for the first time and it fights you. Deflate it, blow it up again, and it's easy. The rubber's already been stretched. Right now, underneath one of the most densely populated volcanic calderas on Earth, that same thing may be happening to solid rock. In 1538, it took roughly 16 meters of ground uplift to finally crack the crust open and produce Naples' last eruption. Today, we've only risen about 4.5 meters. That should be reassuring. According to the scientists who actually study this volcano, it isn't, because the rock itself may not be the same rock it was 500 years ago. On the evening of July 31st, at exactly 7:46 local time, the ground beneath Pozzuoli let go. A magnitude 4.7 earthquake tore through the Campi Flegrei caldera, just west of Naples, at a depth of roughly 3 kilometers. Within minutes, power was out across several neighborhoods. Trains stopped running. The port of Pozzuoli shut down entirely, stranding ferry passengers who were trying to reach Poseida and Ischia on one of the busiest travel weekends of the year. By the time officials finished their first round of inspections, dozens of people had been injured, several buildings had been declared unsafe, and a hillside near the Solfatara crater had collapsed, sending boulders crashing down onto parked cars below. In the hours that followed, dozens of smaller aftershocks kept rolling through the area, some strong enough to be felt clearly across Naples itself. Families who normally would have gone straight back inside chose instead to spend the night outside, in cars, in tents, in makeshift shelters set up by civil protection volunteers, simply because nobody could guarantee that a second strong jolt wasn't coming. Within days, the number of people displaced from damaged or condemned buildings in Pozzuoli alone climbed into the hundreds, and kept climbing as inspectors worked through the backlog of structures still waiting to be checked. This wasn't just another tremor in a region that gets plenty of them. According to Italy's own Geophysical Institute, this was the strongest earthquake ever recorded at Campi Flegrei since continuous instrumental monitoring began. Not the strongest in a decade. Not the strongest since the last major crisis. The strongest, period, in the entire history of modern seismic measurement at this volcano. It surpassed 2 magnitude 4, 6 events that had already been setting records back in 2025, and it happened in a place where roughly 500,000 people live inside or immediately beside the caldera itself. To understand why a single earthquake carries this much weight, you have to understand what's actually happening underneath that ground. Campi Flegrei isn't a mountain. It doesn't look like Vesuvius, looming over the bay with an obvious summit and an obvious crater. It's a vast, mostly flat depression, roughly 8 kilometers across, dotted with more than 20 smaller craters and vents. It's the collapsed remnant of eruptions so large they're almost impossible to picture. One of them, tens of thousands of years ago, is estimated to have been among the largest volcanic events in European history. The last time it actually erupted was in 1538, when a hill called Monte Nuovo rose out of the ground in the space of about a week. That eruption didn't come without warning. Historical records describe roughly a century of gradual ground uplift and repeated earthquakes in the area beforehand, a slow build that locals apparently learned to live with, right up until the ground finally split open near the town of Pozzuoli and threw up an entirely new hill almost overnight. Nobody living through those final days had any modern instruments to tell them how close they actually were to that outcome. Since then, Campi Flegrei has mostly stayed quiet on the surface, but underneath, it never really stopped moving. The ground here rises and falls in a process scientists call bradycism, slow seismic movement driven not by magma pushing directly toward the surface, but by heat and gas and pressurized fluid working their way up from deep below. After the 1538 eruption, the ground spent centuries slowly sinking. Then, around 1950, it started rising again. There was a sharp uplift crisis between 1969 and 1972. Another one between 1982 and 1984. This one's severe enough that authorities evacuated roughly 40,000 residents from the town of Pozzuoli as a precaution. No eruption followed either time. The ground eventually settled, the earthquakes died down, and life went back to something like normal. Then, in 2005, the uplift started again, and this time it never really stopped. For nearly 2 decades now, the ground near Pozzuoli has been climbing, slowly, in fits and starts, punctuated by swarms of small earthquakes that occasionally produce something larger. The total rise since 2005 is now well over 1.5 meters. Just in the past year and a half, the ground has climbed another 30 centimeters. The rate has varied, speeding up, slowing down, speeding up again, but the underlying trend has been unmistakably upward, and the number of earthquakes accompanying that uplift has grown right along with it. So when the magnitude 4.7 hit on July 31st, it didn't come out of nowhere. It came at the tail end of a multi-year acceleration that scientists have been tracking closely, earthquake by earthquake, millimeter by millimeter. What made this one different wasn't just its size, it was what it did to the ground itself. Italy's geophysical monitoring network runs dozens of GPS stations across the caldera, constantly recording the exact position of the Earth's surface down to fractions of a centimeter. In the days immediately following the earthquake, several of those stations, positioned in the central part of the caldera, recorded something unusual. It wasn't just the shaking that showed up in the data. The ground itself had moved. Not temporarily, the way it might shudder and settle back during a tremor, but permanently into a new position. Some stations shifted sideways by 1 to 3 centimeters. One station, near the historic center of Pozzuoli, moved horizontally by close to 3 centimeters and dropped vertically by 1 to 2 centimeters. These are small numbers on paper. In the context of a stressed volcanic crust, they are not small at all. This is where the scientific conversation gets genuinely interesting, and where a real disagreement has opened up among people who study this volcano for a living. The Official Monitoring Institute has been clear that these co-seismic shifts don't change the underlying story. Their position is straightforward. The long-term uplift rate hasn't changed, the carbon dioxide flux hasn't changed, the estimated depth of the magma hasn't changed, and a single earthquake, even a record-setting one, isn't enough on its own to signal a shift into some new phase of activity. By that measure, everything continues to fit the pattern that's been building since 2005. But at least one experienced volcanologist, someone who has spent decades observing this exact caldera, has pushed back hard on that framing. His argument isn't that the sideways shift proves an eruption is imminent. He's been explicit that it doesn't prove that. His argument is narrower and in some ways more unsettling. He says that when a chunk of stressed, fractured crust moves permanently during an earthquake, that movement is itself a piece of information about the condition of the rock, about how close it is to failing, and where the weak points are. Treating it as background noise to be filtered out of the long-term deformation trend, in his view, throws away exactly the kind of detail that tells you something about the structural health of the lid sitting on top of this pressurized system. Whether or not you find that argument fully convincing, it's a legitimate scientific dispute about how to weigh different kinds of data, not a case of information being kept from the public. The shift itself is documented in the Institute's own weekly bulletins, sitting right there in the same reports that explain why officials don't think it changes the bigger picture. That last point matters, because the criticism aimed at the Monitoring Institute isn't really about secrecy. It's about pace. Right now, the public gets updates through weekly bulletins, supplemented by monthly and yearly summaries that roll everything together into broad trends. Critics argue that in a system capable of shifting quickly, a weekly snapshot isn't fast enough to actually reassure anyone, or to warn them in time if something does start to change. Their preferred alternative sounds almost mundane by comparison to the drama of an eruption debate. Publish the raw uplift velocity and the estimated depth of the pressure source continuously, the same way a financial market publishes live prices, so that residents and researchers alike can watch the trend for themselves in near real time, rather than waiting days or weeks for an official summary to catch up with what the ground has already done. To understand why either side of this argument matters, you need to understand what's actually sitting underneath Pozzuoli. Most researchers now believe the pressure driving this uplift isn't coming from a shallow pool of molten rock sitting just beneath the surface, ready to erupt. It's coming from something more like an enormous underground plumbing system. Deep magma, several kilometers down, continuously releases hot gas. The gas rises and interacts with groundwater trapped in the volcanic rock above it, heating it, pressurizing it, and creating what amounts to a vast hydrothermal reservoir extending through roughly the upper 2 to 3 kilometers of the crust. Heat water inside a sealed space, and it wants to expand. If it can't, the pressure builds. That buildup, many scientists believe, is what's been pushing the ground upward for the past 20 years. If that pressure eventually exceeds what the overlying rock can withstand, the most likely first outcome isn't a classic lava-spewing eruption. It's what's known as a phreatic eruption, a sudden, violent release of steam and pressurized water, blasting through the rock above it and hurling fragments of that rock outward at extremely high speed. No fresh magma needs to reach the surface for this to happen. It's essentially a pressure cooker failure, and it can happen with very little warning. Here's the part that tends to get lost when people talk about this scenario. A phreatic eruption sounds, on the surface, like the smaller, more survivable option compared to a full magmatic eruption. And in isolation, it often is less destructive. But at Campi Flegrei specifically, researchers who study the volcano's eruptive history point out that the overwhelming majority of past eruptions here didn't stay purely phreatic. They evolved. A violent steam explosion can suddenly depressurize the shallow system above it, and that sudden pressure drop can act almost like a pump, helping draw magma upward from greater depth. What begins as a steam-driven blast can, in some cases, develop into something that involves magma more directly. In other words, a phreatic eruption isn't necessarily the end of the story. Historically, at this particular volcano, it's often been the opening act. One of the signals researchers watch closely for evidence of deep magmatic activity is carbon dioxide. It's highly mobile. It escapes easily when pressure drops, and its presence at the surface in places it shouldn't be, old railway tunnels, school basements, residential cellars, has been increasing. People in some of these areas have reported feeling dizzy or unwell simply from being in enclosed spaces where gas has accumulated. Researchers interpret the sustained, increasing arrival of this gas as consistent with a deep magmatic system that isn't just sitting static, but is being continuously replenished by fresh material moving upward from depth. It doesn't mean an eruption is coming soon. It does mean the system underneath this city is not dormant. Researchers monitoring these gas readings have also been careful to separate two very different depths of activity. Most of the earthquakes recorded during recent swarms originate in the upper 3 kilometers of crust, some barely a kilometer down, which is exactly the zone where instruments can see clearly and where the hydrothermal system is doing most of its work. The main magma reservoir feeding that system is generally placed much deeper, somewhere in the range of 7 to 8 kilometers down, though a handful of studies have suggested smaller pockets of pressurized material sitting shallower still, closer to 4 kilometers. Scientists studying the volcano are quick to caution against treating every one of those shallower estimates as a settled fact, since the imaging techniques involved are still being refined and debated within the field itself. Now let's go back to the balloon. This is the argument that, in my opinion, deserves the most attention, and it's the one that ties everything else together. Before the 1538 eruption, the ground beneath Campi Flegrei is estimated to have risen by something in the range of 16 meters over roughly a century before the crust finally gave way. Since the current uplift phase began around 1950, cumulative rise is only about 4.5 meters. On the surface, that comparison sounds reassuring. If it took 16 meters last time, and we're nowhere close to that now, surely there's a wide margin of safety. The problem with that comparison is that it assumes the rock today has the same strength it had 500 years ago. It probably doesn't. Over the past several decades, the upper few kilometers of crust beneath this caldera have been repeatedly heated by rising gas, repeatedly stressed by uplift, and repeatedly fractured by earthquake after earthquake, including 3 separate major unrest episodes since the 1950s. Every one of those episodes leaves a mark. Rock, like rubber, has elastic limits, and those limits change with repeated use. Multiple independent studies have found that the caprock sitting above this hydrothermal system has lost a significant portion of the mechanical strength it had just a few decades ago. Some estimates suggest it retains only a fraction of what it had in the 1980s. If that's accurate, then the 16-meter threshold from 1538 tells us very little about what it would actually take to crack this same rock open today. The failure point itself may have moved. This is precisely the kind of detail that makes those small, permanent ground shifts from the July 31st earthquake worth taking seriously, even if they don't prove anything on their own. If the crust really is more brittle and more fractured than it used to be, then understanding exactly how it responds when it's struck by a large earthquake, where it moves, how much, and in which direction, becomes directly relevant to understanding how much closer the whole system might be to a structural failure. That's the essence of the disagreement over how this data should be treated. It's not a fight over whether the numbers are real. It's a fight over how much they matter. It's worth being precise here about what none of this means. No credible scientist studying Campi Flegrei is claiming that an eruption is imminent or that this particular earthquake proves magma has broken through toward the surface. The evidence simply isn't there. What researchers are saying consistently across multiple independent voices is that an eruption cannot be ruled out, and that the trajectory of the past 20 years, accelerating uplift, increasing seismic energy, rising gas emissions, degrading rock strength, is not a trajectory anyone should be comfortable ignoring. There's a real difference between this is definitely going to erupt and this is not something we can afford to dismiss, and the second statement is the one that keeps showing up in the actual scientific literature. That uncertainty is, in some ways, the hardest part of this entire story, because it's the part that lands directly on the 500,000 people who live above this system every single day. Unlike a hurricane, which meteorologists can often see coming days in advance, volcanic unrest doesn't come with a reliable countdown. Phreatic eruptions in particular can occur with almost no warning at all. Emergency planning for this region has long been built around the assumption that scientists would be able to identify a window of roughly 72 hours before a major eruption, giving authorities time to evacuate the highest risk zones. Given everything we've just discussed about how quickly a hydrothermal system can fail, some researchers now openly question whether that assumption is realistic. And even setting aside the timing question, there's a deeper, more uncomfortable dilemma buried in here. Imagine, hypothetically, that scientists estimated a 10% chance of an eruption within the next month. 10% sounds low. Most people wouldn't cancel a vacation over 10% odds. But apply that same number to a decision about evacuating 500,000 residents, uprooting them from their homes, their jobs, their schools, scattering them across the country with no fixed date for return, and 10% starts to look very different. Some researchers have argued that even that level of risk might be too high to responsibly tolerate, given the stakes involved. But flip the number around, and it also means there's a 90% chance nothing happens at all, and that the evacuation itself becomes the disruption people remember, rather than the disaster it was meant to prevent. There's no politically comfortable answer buried in that math, and it's part of why officials have historically leaned toward reassurance rather than dramatic action, even during periods of heightened activity. Then there's the question of what these buildings can actually survive, which turns out to be almost as uncertain as the volcanic question itself. Campi Flegrei's earthquakes tend to be shallow. The July 31st event struck at only about 3 kilometers depth, and some of the more recent swarms have originated even closer to the surface than that. A shallow magnitude, 4 didn't 4. 7 doesn't behave like a deeper earthquake of the same size. It can produce disproportionate shaking directly above the source. In a city built up over generations, much of it before modern seismic building codes existed. Some researchers have pointed out that a comprehensive, building-by-building vulnerability assessment across the region, including private housing stock, still hasn't been completed, even after years of escalating seismic activity. That's a genuinely uncomfortable gap. It means that beyond the volcanic uncertainty, there's a more immediate and more answerable question hanging over the region. If another strong, shallow earthquake strikes tonight, are the specific buildings people are sleeping in actually able to withstand it? For a meaningful number of structures, nobody currently seems to have a confident answer. This is why some scientists have started proposing solutions that sound almost unrelated to volcanology at first, but are really just an attempt to manage risk on a longer timeline than any single evacuation order ever could. Rather than waiting for a crisis and then trying to move 500,000 people out of harm's way in a matter of days, the argument goes, authorities should be working now to gradually and voluntarily reduce the permanent resident population in the highest risk areas. Stop issuing new building permits in the most exposed zones. Offer economic incentives for people to relocate elsewhere in the region over time. Let tourism continue, since visitors can leave quickly if conditions change, but slowly shrink the number of people whose entire lives are rooted directly above the most hazardous part of the caldera. It's not a popular idea, understandably. People don't want to be told to leave homes their families have lived in for generations, especially without a clear deadline or a clear threat. But the reasoning behind it is straightforward. If a genuine crisis does eventually arrive, the size of the population you'd need to move in a hurry is the single biggest factor determining how manageable, or how catastrophic, that response ends up being. History here backs that logic up. In 1970, residents were evacuated as a precaution and no eruption followed. In 1984, 40,000 people were moved, and again, nothing happened. Both times, officials had to make the difficult call to send people home without absolute certainty that the danger had truly passed. Today, with a larger population living in the caldera than existed during either of those earlier crises, that same decision, should it ever need to be made again, would be significantly harder to manage. The frustration among residents isn't hard to find. People whose homes have been declared unsafe are struggling to find anywhere else to rent, in a housing market where landlords, sensing sudden demand, have simply raised their prices. Roads remain partially closed. Evacuation routes run directly past buildings still waiting on structural inspections. Property values in the most affected neighborhoods have dropped, tourism bookings have slowed during what should be peak season, and small businesses that depend on that seasonal income are closing their doors earlier than usual. For the people who haven't lost their homes but live next door to someone who has, there's a different, quieter kind of unease. The sense of watching a damaged building across the street every single day and wondering whether the next moderate earthquake will be the one that brings it down. None of that requires any eruption to become a genuine daily hardship. It's already happening right now, driven entirely by earthquakes that, geologically speaking, are still considered comparatively minor. None of this is meant to suggest that a catastrophic eruption is around the corner or that people should be panicking. Even researchers who take the risk seriously tend to agree that if an eruption does eventually happen, the most likely scenario resembles something closer to the 1538 event. A localized eruption, producing a new, small volcanic landform, not the kind of massive ash-bearing explosion sometimes associated with the word supervolcano in popular imagination. But the crucial difference between 1538 and today isn't the likely size of a future eruption. It's what's sitting on top of the caldera now that wasn't there 500 years ago. Roads, rail tunnels, a working commercial port, hundreds of thousands of homes, schools, hospitals, an international airport nearby. Even a comparatively modest eruption in a landscape this densely built and this heavily populated could create a genuinely enormous emergency, simply because of how much infrastructure and how many people now occupy the ground where any new vent might open. And that's really the honest summary of where things stand right now. The July 31st earthquake didn't prove that Campi Flegrei is about to erupt. It didn't prove that magma has broken through toward the surface, and no serious scientist is claiming that it did. What it did do is produce the single largest release of seismic energy this volcano has generated since instrumental monitoring began, and it left behind small, permanent, well-documented shifts in the ground that different experts are now interpreting in different ways. The underlying uplift trend hasn't changed. The rate of gas emissions hasn't changed, but the crust beneath one of the most densely populated volcanic regions on the planet has now been stretched, heated, and fractured for the better part of 2 decades straight, following 3 earlier stretching cycles across the previous 70 years. Nobody, including the scientists who study this volcano for a living, can say with confidence exactly how much more stretching that rock can take before something gives. What they can say, with real confidence, is that the answer today is almost certainly not the same as it was in 1538. The balloon has already been blown up before, and every time you blow it up again, it gets a little easier to do. Whatever happens next at Campi Flegrei, the honest scientific position right now sits in that uncomfortable space between reassurance and alarm. Not an imminent eruption, but not nothing either. It's a slow, decades-long process being watched in real time, argued over in real time, and lived through in real time by hundreds of thousands of people who wake up every morning on top of one of the most closely monitored and least predictable pieces of ground on Earth.